Welcome everyone to the first video lecture for PT 5432, Motor Control and its Clinical Applications. In this first lecture, I'll try to provide some important background material and some context for appreciating the material you will be studying throughout the semester. The textbook in this class is written by Anne Shumway-Cook and Marjorie Woolacott. The material covered in today's lecture overlaps with the material presented in Chapter 1 of the textbook, and I have been using the 5th edition of the textbook for putting together these lectures. Coming into this class, I'm sure a reasonable number of you will be asking, what is a class on motor control about? There's two equally legitimate answers to this question that depend upon the particular viewpoint that you take. The first viewpoint is a little bit more abstract and theoretical. From this viewpoint, a class on motor control is about understanding the ability to regulate or direct the mechanisms essential to movement. The second viewpoint is a bit more pragmatic and functional. From this viewpoint, a class on motor control is about understanding the ability of a specific person that is embedded within a real-world setting to accomplish a meaningful goal. Sitting behind much of the knowledge that you'll encounter during this class are various theories of motor control. When I talk about a theory of motor control, I am simply referring to a group of abstract ideas about how movement is controlled. A reasonable question to ask when coming into a class like this is, why are there different theories of motor control? Different theories often reflect different ideas about the key principles that allow us to understand how functional movements are organized. Different theories also reflect different opinions about the relative importance of the key principles that you will encounter. Let's think about this issue in the context of two concepts that are fundamental to the practice of physical therapy. Disablement concerns the impact of a disease on human functioning at many different levels. What can a theory of motor control do for us when it comes to the concept of disablement? One thing a theory of motor control can do is help us to conceptualize what we mean by the word functioning. For example, what goes into an understanding of a person having high functioning or low functioning? What are the things that affect function? What is the relationship between functioning and a specific functional assessment that we might perform, like a simple range of motion, for example? Rehabilitation concerns therapeutic interventions aimed at optimizing function and therefore maximizing participation. Here, a theory of motor control can be valuable in helping us to understand why an effective intervention is effective. It can help us in providing principles upon which to base new interventions, and it can be useful in providing a framework for assessment. Today, we're going to briefly look at some of the theories that influence how we understand motor control. These include reflex theory, hierarchical theory, neuromaturational theory, motor programming theory, and systems theory. Let's start off with reflex theory. And looking at reflex theory, let's start off looking at some simple examples of reflexes. Here we see a person holding a cup. They have their eyes closed, and then someone comes along and pours some water into the cup. What do we see? When we look at the arm angle, we see a slight extension of the arm following the water being poured into the cup, and then we see the arm returning to its original position. When we look at the associated EMG patterns, we see two distinct spikes in the plot, one occurring at around 30 milliseconds after the water being poured in, and a second one occurring at around 50 milliseconds. The spike at 30 milliseconds is known to be associated with the monosynaptic stretch reflex. This reflex functions to help maintain the muscle at a constant length. In this reflex, a muscle spindle in the biceps responds to muscle lengthening, and we get an afferent signal sent into the spinal cord, represented by the blue line in the figure. The afferent signal has an excitatory connection back into the biceps. This increases biceps alpha motor neuron activity and causes biceps muscle fibers to contract and to bring about a resistance to the stretching. There are interesting subtleties to this reflex. The afferent signal that we see going into the spinal cord also has connections to antagonist muscles, such as the triceps. Inhibitory interneurons decrease alpha motor neuron activity to the triceps. Another component of this reflex that we haven't depicted is the action of gamma motor neurons. Gamma motor neurons regulate how sensitive the stretch reflex is by tightening or relaxing the fibers around the spindle. Here we see the EMG activity of the biceps brachii again. The second spike at 50 milliseconds is related to the long loop functional reflex. In this reflex, afferent information resulting from the muscle stretch loops through the higher segmental levels of the spinal cord and the brain. The human motor cortex is deeply involved in the regulation of reflexes, and this is one example. Loops like this one appear to add flexibility to the human stretch reflex, allowing it to adapt across a range of functional tasks. Let's look at an example of this in action. Here we see the same setup as before. A person is holding a cup out in front of them. This time, though, we're going to change the task. Rather than telling the person to hold the cup still, we tell them that if water gets dumped into the cup while they're holding it and they have their eyes closed, they should let the arm be moved. In this situation, what we see is that when water is dumped into the cup, the arm extends with the load. Let's look at the EMG activity that's associated with this in this modified task. We still see a spike at 30 milliseconds that's associated with the monosynaptic stretch reflex that we looked at on the previous slide. But the spike associated with the long loop reflex has now gone. What we see here then is that the long loop reflex is under voluntary control. A change in intention, performing a different task, can flexibly modulate this aspect of the reflexive response. To use other language, the long loop functional reflex is a volitional response. We just looked at some examples of reflexes. But what is the reflex theory? Charles Sherrington was one of the most influential developers of reflex theory. He attempted to create a theory of all human behavior that was entirely based upon the concept of reflexes. In this theory, reflexes are the building blocks of complex behavior. We won't go into it here, but Sherrington's theory goes far beyond the simple reflexes that we've looked at on the previous couple of slides. To gain a simple understanding of it, in Sherrington's reflex theory, behavior can be understood to be the result of an organization of many reflexes that become variously associated with each other and with environmental contingencies. Part of the subtlety of Sherrington's theory relates to the subtle things that can act as environmental contingencies, such as a slight change in environmental context. Through the class, you'll see examples of the important role reflexes. Even though reflexes alone cannot realistically provide a functional behavior, they provide an important. So, what are the limitations of a reflex theory? What are the limitations of a reflex theory of behavior? Does not explain how a movement might be initiated. Does not explain how a movement might be initiated stimulus or something. Independent of an initiating stimulus or something. The theory explicitly excludes. In other words, the purely voluntary and spontaneous behavior. Purely voluntary and spontaneous behavior. Relatedly, the theory does not adequately explain and predict. The theory movement does not adequately explain and predict movements that occur in the absence of a sensory stimulus. Next. The reflex theory struggles to explain movements where sensory feedback that is not possibly be fast sensory feedback could not possibly be fast enough. An example of this would be trying to account for a person's ability to touch type. Lastly, the reflex theory begins to get quite convoluted. The reflex theory begins to get quite convoluted when it tries to explain how a single initiating response can result, for example, in varying responses. Trying to explain how you have a reaction of withdrawing your hand from a fire in one case. Your hand from a fire. This reflex can be completely changed. This reflex can be completely changed. Your child in the case in a fire. You're trying to stop your child being burnt in a fire. Next, let's think about the clinical implications that can be drawn from the reflexive theory, the reflex theory of motor control. In the context of assessment, the form and function of a particular observed movement pattern can be interpreted in terms of the presence or absence of controlling reflexes. From this perspective, a valuable part of a functional assessment is going to be the assessment of normal and abnormal reflexes. In the context of treatment, the suggestion of the reflex theory of motor control is that your focus should be on enhancing or reducing, that is, appropriately modifying, the effect of various reflexes during motor tasks. We won't get into the topic of treating reflexes in this class, but it's worth mentioning some of the basic challenges of treating reflexes that can be concluded from properly understanding the notion of a reflex. As we mentioned before, part of Sherrington's theory was about how the stimulus for a particular reflexive response can be very specific to a very particular situation. Because of this, an important issue to consider when working with reflexes is whether the stimulus that's being provided in the clinic has the same characteristics as the naturally occurring stimulus. Next, we have the hierarchical theory. The hierarchical theory overcomes the major limitations of the reflex theory by emphasizing top-down control. For example, in this theory, higher centers of the central nervous system control or regulate lower levels. In this particular theory, bottom-up control, such as when a tug on the arm elicits a monosynaptic reflex, is never truly the cause of a functional movement. This theory suggests that the basic style of organization of the nervous system is a hierarchy of descending commands. This theory suggests that motor control emerges from reflexes that are nested within hierarchically organized levels of the central nervous system. A key point in this theory is that meaningful movements are first generated spontaneously, and then after that they begin to be further regulated by external stimuli. So what are the limitations of the hierarchical theory? The hierarchical theory cannot explain the dominance of reflexive behavior in certain situations. For example, the presence of a withdrawal reflex in response to a painful stimulus. Another limitation is that it's inappropriate to assume that all primitive reflexes are immature and unadaptive. Let's look at some of the clinical implications of the hierarchical theory. The hierarchical theory can be used as a pretty good explanation of disordered motor control in patients affected by stroke and cerebral palsy. We can interpret the effect of a CVA in terms of damage to higher centers and then lower centers consequently acting to control movement. In other words, cortical inhibition is lost, leading to so-called pathological reflexes. The hierarchical theory is also the motivation for traditional PT treatment approaches for stroke and cerebral palsy, developed by Bobarth and Brunstrom. An example of an influential application of the hierarchical theory is the neuromaturational theory of development. In the neuromaturational theory, motor control is theorized to emerge from reflexes that are nested within hierarchically organized levels of the central nervous system. According to the neuromaturational theory, the typical development of lower-level reflexes is followed by an increased corticalization, leading to higher-level control over those reflexes. The neuromaturational theory of development suggests that primitive reflexes are important until voluntary control emerges. Here we see pictures of the Moro reflex. The Moro reflex is a startle reflex and is elicited with stimuli such as loud noises. It is characterized by extension of the arms and legs away from the body and to the side, and then by drawing them together as if in an embrace. The Moro reflex is easily elicited with a slight drop of an infant's head relative to its body axis, when the infant's laying in the supine position. The neuromaturational theory of development proposes that the disappearance of the Moro reflex is related to the achievement of head control. Similarly, reaching is believed to emerge after the grasp reflex becomes integrated into hierarchical control. In simple terms, the neuromaturational theory predicts that the progressive appearance and disappearance of reflexes will occur through development, as the child moves through different developmental stages. A key limitation of the neuromaturational theory is that this theory assumes that the maturation of the central nervous system is the exclusive determiner of change in the form and function of behavior during development. And there's multiple sources of evidence that directly contradict this. Modern theorizing about motor control now recognizes the fact that each level of the nervous system can act on other levels, and that the interaction between levels varies depending upon the task. Within modern theories, reflexes are now seen as one of many processes that are important for motor control. The next theory of motor control for us to consider is motor programming theory. Instead of reflexes, as in the reflex theory, the fundamental units of functional behavior in this theory are centrally generated motor patterns. A motor program could be a set of neural connections that are hardwired. One of the simplest examples of this is shown on the right. This is a very simple, hardwired organization of cells that is able to produce rhythmic patterns. Very simple rhythmic pattern generating networks like this one have been shown to be a key part of the functional organization of animal locomotion. Motor programs may also be a set of rules stored in higher centers that represent actions in more abstract terms. One of these higher areas is the supplementary motor cortex. We will go into detail regarding motor programming theories towards the end of the semester. But for now, let's look at two observations that have helped motivate this theory. The first observation comes from an animal research study. This study looked at facial grooming behaviors of rats. Here we see a rat grooming its face. It wets its hand with its tongue, and then it wipes its head. In this study, some of the rats had their forearms surgically removed. The basic finding of this research was that after recovering from the surgery, the rats were still observed to produce coordinated movements of their upper arms. The observed movements were consistent with the movement patterns that they had learnt when the limb was intact. What is theoretically interesting here, in the context of understanding a reflex theory, is that grooming patterns could be produced in the absence of typical sensory feedback from the missing limb. For example, from the sensation of the hand making contact with the tongue. This kind of connection would be the basis for a reflex theory-based explanation of this behavior. The implication of this study is that complex patterns of action can be produced in the absence of sensory feedback. The motor programming theory explains this as a consequence of there being an internal motor program for grooming. The second source of evidence that supports the central tenet of motor programming theory comes from a famous case study. Ian Waterman, seen depicted here, had a severe bout of gastric flu at the age of 19. During this illness, his body produced antibodies to the infection he had, and these antibodies attacked his nerves. As a result of this, Ian permanently lost all touch and sense of movement and position sense below the neck. So what did this mean functionally for Ian? In simple terms, it meant that if Ian had his eyes closed, and you walked up to him, took hold of his wrist and lifted up his arm, he would not know that it happened. Initially, without peripheral feedback from his limbs, Ian could not move in a controlled way at all. He was effectively paralysed. His paralysis was not by weakness, but by the absence of any ability to make ordered movement. I highly recommend reading one of the books written about Ian from the author Jonathan Cole, or watching one of the documentaries that have been made about him. At the time of making this video, the documentary film "The Man That Lost His Body" can be found on the website documentaryheaven.com with the web address shown here. Although Ian could not initially move his body in a controlled way, he managed to train himself to control his posture. He managed to train himself to reach and grasp objects and to walk. Ian is one of the few people in the world affected in this way that actually have actually managed to teach himself to walk. We'll look at Ian a little bit more later in the semester. For now, I want you to think about the implication of Ian's astounding ability. Ian was able to teach himself to walk. This gives us an example of motor control being possible without haptic sensory feedback, without proprioception. The basic implication we have here is that we can see from Ian that top-down control of human action is possible. What are the limitations of the motor control theory? The main point to consider is that a central motor program cannot be considered to be the sole determiner of functional movement. To understand this point, we can again look at the case of Ian Waterman. Ian can stand, Ian can walk, Ian can gesture, but all of these amazing accomplishments are very impoverished versions of the actions of a young, healthy adult with intact proprioception. Ian has no haptic perception from the neck down, and he had to spend a lifetime teaching himself to regain the ability to perform various activities of daily living. So, what do Ian's abilities look like on a good day? If you turn the lights off in a room that he's standing in, Ian will not be able to maintain his balance for very long at all, and if he cannot see the ground and his legs, he's unable to walk. In the real world, Ian is unable to walk without studying the ground in front of him, and then explicitly planning how to negotiate that particular part of the environment. Ian can stand and walk on stable level surfaces, but if you ask him to do a task like walking across a pebble beach, all bets are off. Ian has to think about every single action he performs, and he pays direct attention to that action as he performs it. If you distract Ian, his ability to act is seriously impaired. So, what are the clinical takeaways from the motor programming theory? The motor programming theory is important as it has allowed clinicians to move beyond a purely reflex-based explanation of disordered motor control. Motivated by this theory, clinicians have moved beyond inhibiting reflexes and reducing spasticity to improve motor control. Motor programming theory suggests the importance of helping patients to relearn the correct rules for an action. The next clinical implication is that motor programming theory suggests that interventions should focus on retraining movements that are important to the functional task at hand. Lastly, motor programming theory has motivated interventions based upon mental rehearsal of actions. The study of interventions based upon mental rehearsal has shown that you can get real functional improvements in certain circumstances purely based upon mental rehearsal of the action. The last theory we'll look at today is the systems theory. The systems approach provides a useful framework for organizing existing knowledge in the field of motor control. We will be using the systems framework to organize the content of this class. The central prediction of the systems approach is that movement emerges from the interaction of three large-scale factors. These factors are the task, the individual, and the environment. The version of the systems approach you will learn is the systems approach developed by the authors of the textbook, Anne Shumway-Cook and Marjorie Willicott. In this theory, functional movement is understood to emerge from the interactions of the many factors that are known to be important to motor control. In their model shown here, the various factors that are believed to support effective motor control are organized into functional subcategories. Right at the center of the model, we have the letter M. M stands for the movement pattern that emerges. Surrounding M, we have three overlapping circles, representing different sets of constraints that are combining to affect and to influence the particular movement pattern that emerges. T stands for task, and is split into three core functional task attributes: the ability to regulate posture, the ability to be mobile in the environment, and the ability to manipulate objects in the environment. I stands for individual, and captures the various functional subsystems within the individual that support effective motor control. This includes motor capabilities, sensory capabilities, and cognitive capabilities. Lastly, we have E. E stands for the effects of the environment. This captures the aspects of the environment that are incorporated into the functional organization of an action. When we look at M at the center, we see that movement emerges from the subset of constraints contributed by T, I, and E, by the task, by the individual, and the environment. Over the next couple of slides, we will review the key concepts in this model. Let's start out by looking at the subsystems within the individual. There are three primary factors within the individual that constrain movement: action, perception, and cognition. The term action includes the effects of body mechanics and the functional motor contributions of various neural structures, such as the peripheral nervous system, the cerebellum, the basal ganglia, the motor cortex, and the primary motor cortex. Body mechanics relates to the mechanical constraints of the body that are relevant to action. You already understand this idea a little bit from the biomechanics class we had last semester. One of the ways movement can be simplified is by exploiting mechanics. That is, by working with the physics of the body. By doing this, you can dramatically decrease the work that the central nervous system needs to do to control a movement. Put another way, you can decrease the number of degrees of freedom that need to be actively controlled. Next, we have perception. Perception encompasses the detection of action-relevant information. This includes auditory, vestibular, and haptic information. The term haptic encompasses various aspects of body-based perception, including touch and proprioception. Throughout this class, we'll see multiple examples of how perception facilitates effective motor control. A simple example of the importance of perception can be seen in designing interventions in children with visual deficits. In many cases, simply using a magnifier can produce the visual information needed to allow the child to improve their fine motor coordination. Lastly, we have cognition. This includes factors such as attention, motivation, emotion, learning, and memory. Children with autism and developmental coordination disorder have associated cognitive problems such as poor attention span. Patients affected by traumatic brain injury can have difficulty learning new tasks, but can often do the tasks they used to do before the injury just fine. This here is an example of how motor impairments can be related to memory impairments. When attempting to understand how the attributes of a task can affect motor control, the first step is to appreciate the particular combination of stability, mobility, and manipulation constraints. Sitting, for example, requires the regulation of body posture in a chair. Walking requires the stabilization of body posture relative to gravity, while also controlling the motion of the body relative to the environment. The task of walking while carrying a cup of coffee has all of the constraints of walking, with the added constraints of manipulating the cup in a way that keeps the coffee in the cup. So in these progressively complex examples, we see how combinations of constraints lead to defining the task demands. We can also consider other task attributes. A task can be more open or more closed. A more open task is open to the influence of multiple constraints. In a game of football or soccer, a complex set of factors shape the movement patterns that are organized to satisfy the demands of the game. Those demands can change moment to moment in the game of football. Closed tasks have a comparatively closed context of constraints. Here, to provide a contrast to a game of football, we see a game of soccer swing ball. In this game, you kick the tethered ball, and the tethered ball will reliably swing around the pole and return to you. Unless the tether snaps, the demands of the task are not going to fundamentally change. Environmental constraints on movement can be split into regulatory features and non-regulatory features. Regulatory features are those features of the environment that constrain the form and function of movement. Here we see different ground surfaces that affect how the foot must act to support walking. Here we see different inclined surfaces that place different demands on how the body can be postured in order to ascend these slopes. Here we see different tools that place different demands on how they can be manipulated. Similarly, here we see different mugs that have different features that differently constrain how they can be acted upon. In all of these cases, we're seeing that the characteristics of the environment are constraining, are forcing the body to have to act in a particular way in order to interact with that part of the world. Non-regulatory features are those features of the environment that can affect motor behavior, but that movement does not have to conform to them. For example, here we have a do not walk sign and a keep off the grass sign. These parts of the environment can constrain our actions, but we do have the freedom to not conform to them. The systems theory suggests that if you understand more and more about the various constraints that come together to influence the form and function of the movement, you can make use of this knowledge to help patients regain motor function. If the movement patterns that you observe in the clinic emerge from the context of constraints, then the key implication of the systems theory is that you need to be aware of the changes in the context of constraints session to session. Let's look at some more clinical implications of the systems theory. To assess patient functionality, therapists need to observe the degree of patient success in completing a task over systematic manipulations of task-relevant constraints of the individual, task-relevant constraints of the environment, and task parameters. Such knowledge allows for the identification of the specific contexts in which a person can always accomplish the task, sometimes accomplish the task, or never accomplish the task. I want to finish up this brief consideration of the theories that influence modern thinking on motor control by looking at the relationship between the systems theory of motor control and the World Health Organization ICF framework. Before we do this on the next slide, I want to remind you of two distinctions that exist in the international classification of function. The first distinction is between activity and participation. The term activity in the ICF model refers to the capacity of a particular person to be able to execute a particular task or action. The term participation, in contrast, refers to the capacity of a particular person to be able to be involved in a life situation that's meaningful to them. Activity and participation capture two aspects of function. Activity looks at the individual. Participation looks at the individual embedded in a social situation. The second distinction that I want to review is that between capacity and performance. Capacity refers to ability as it exists in a standardized or uniform environment. Performance, in contrast, refers to ability as it exists in a person's actual life situation, in an actual environment. In the ICF model, factors that impact on functioning are classified. At the lowest level, function is characterized with respect to the structures of the organism and the functions that are expressed by those structures. Dysfunction at this level is seen as impairment, where impairment represents a change in body structure and an associated change in the functions expressible by that structure. When we look at the corresponding aspects of the systems model, we have the structures in the individual relevant to motor control, represented by I subscript S, and the functions expressed by those functions, represented by I subscript F. At the next level in the ICF framework, function is characterized by the activities expressible by an individual intending to perform a specific task in a specific controlled environment. Dysfunction is characterized by changes in the activities that can be performed. When we look at the corresponding aspects of the systems model, we have three sets of interacting constraints. We have the constraints of the individual, represented by the structures in the individual relevant to motor control and their corresponding functions. We also have task constraints, represented here as the blue letter T. The task constraints capture the type of activity to be performed. Lastly, we have the environment in which the task is to be performed. At this level, we represent the environment with the symbol E*. This captures the fact that the environment is not the real world, but is a controlled setting. A parallel here is to think about a patient completing an evaluative test in the controlled environment of the clinic. At the final level, function is characterized with respect to participation and the ability to perform activities in various real-world situations. Dysfunction is characterized by changes in the ability to participate in activities in certain contexts. When we look at what has happened to the systems model at this particular level, we can see that the E* that we had in the middle is replaced by E physical and E social. So E subscript physical and E subscript social. These capture the variations that arise from changes in the physical and social context in which behavior is performed. In the context of assessing a patient, think of the difference between observing a patient walk in the clinic versus observing a patient walk down the aisle of a busy supermarket while looking for a particular item on the shelves. So, on the left we have the ICF framework, and on the right we have the systems theory model. The T, the I, and the E in the systems model capture the complex context of interacting constraints. by virtue of the interaction of these constraints, we get the emergence of a particular movement pattern. The fundamental prediction of the systems theory model is that functional behavior emerges from the interaction of task, individual, and environmental constraints. From the constraint space perspective of the systems theory, we can identify the sets of constraints that are relevant to understanding function, and explore how the interaction of those constraints affects the functioning of the patient. We will look at some of the theories of motor control that we've touched on today in more detail as they become directly relevant throughout the semester. The systems theory model is the theory that provides the framework for the textbook and the lectures, so it's one of the most important parts of this lecture that you should focus on trying to understand. Okay, that's it for this lecture. We'll pick up next lecture by starting to look at the control of posture.